Good evening, everyone. So first, let me thank the organizers for giving us this opportunity to give this keynote speech. So the title of our talk is Teaching Machines to Manipulate Natural Scene Images. And today, I and Erkut will talk about our recent work, which was presented as SIGGRAPH 2020 this last summer. And basically, this is a joint project with our former student, Levent Karacan, and our colleague, Zeynep Akata. So let me just first briefly summarize our motivations behind this project. Basically, we were motivated by two separate things. One was the depiction of nature in novels, like Yaşar Kemal's prose here. And when you read these words, you can immediately start to visualize the corresponding scene in your imagination. And for example, if I make some Google image search, this is as close as I can get, similar to the previous text. So this was our first main motivation. And the second motivation was the famous TV painter, Bob Ross. I'm sure if you are older enough, you can well remember him. And the nice thing with him is that while drawing his paintings, he can also explain his thought process. So let me just play this short clip here.
Right there, big tree. And he's got a friend there. There he is. Okay, let's go on the other side. Maybe over here, there's really some big trees.
So this is nice simply because if you just think about this as a generative process, so basically you are providing some information about the image content. And again, this was the second motivation. So now let me continue a little bit about more like our machinery, the underlying theoretical framework, which is generative modeling of images. So basically, our goal here is to learn the underlying hidden structure of the training images. And the idea is that once you have a model that can best approximate the data distribution, you can sample new samples from your model. And for this purpose, of course, as you might guess, we will be using deep neural networks. So let me just describe what we mean by these neural networks. So for the time being, suppose that we are interested in learning to generate a specific object category, like a cat images. And if we train a model, a generator network, okay, we again try to understand the underlying data distribution. But this is indeed a very hard problem simply because the images are quite high dimensional structured data, and it is not that easy to learn the underlying latent information. But once we have such a model, we can just generate novel samples, like for example, by sampling from a known data distribution, like a Gaussian distribution shown here. In our work, we use the generative adversarial networks framework. So in a nutshell, let me just describe the main idea behind this model. Basically, here we are training not a single network, but two separate networks. One is the generator network and the other is the discriminator. And the learning process is defined as a game between the generator network and the discriminator network. Basically, the purpose of the generator is to fool the discriminator by synthesizing realistic samples, whereas the discriminator tries to distinguish fake samples from the real ones. And just to give you the intuition behind this, okay, I would like to see the discriminator like an art critic, okay? And suppose that the generator network is just an amateur painter. Maybe at the beginning, it is quite easy to distinguish the generated paintings by the generator network. However, based on the losses they optimize, it really gets harder and harder for the discriminator to distinguish between real and fake samples. And at this stage, we are done with training of the generator network. So even if GANs was just proposed about 5 years ago, now it is one of the most popular approaches. And here in the slide, you can see the past progress in the past 5 years. And this one just are using images taken from these papers on GANs listed below. And as you see, the results are really amazing. However, if you ask whether this is a solved problem, can we solve image synthesis? My plain answer is of course not. But of course, we have reached a maturity level. Like for example, here is again another result from StyleGAN 2 paper, which is used to learn to generate human faces. So the data set usually involves just a single person. However, some training images are like close-up images of two persons that are nearby. And because of that, the samples, if you look at the images, may include a second person. Like in this example, if you look at the eyes, the rotation of the eye is quite unnatural. Of course, this depends on the training images used to train this face generator. And I must also add that learning to generate faces is a relatively simpler problem because you almost have a complete alignment between different training images, like the positions of the eyes, the nose, the hair, and so on. And if you look at more harder cases, like for example, these are the results of another recent model called Big GAN. And here you are seeing the samples for different ImageNet classes. Okay, and compared to the one on the left, of course, these seem quite unnaturalistic. Simply because these classes are hard to model. The diversity, the spatial regularities are too different from one sample to another. So these models cannot really capture all the complexities of these different visual categories. And nowadays, recent subcategory behind these generative models is the image-to-image translation models. So you can consider this much like an umbrella term, okay, where the task is this time not to generate a sample from scratch, but from one image or one domain to another. So that's why here the network is called translator, simply because this time we are learning to map images from one domain into another. And this is a really general framework, okay? You can apply this for low level or for high level image processing problems. So, as I said, this is quite general. So here is like a very simple, maybe not a problem that does not require too much semantics, which is super resolution, where the input is a low resolution image and the output is a high resolution image, and the translator just learns to super resolve on the given low resolution image. Or here's another one. This might be a little bit more complex than the previous one, where the input is a black and white image, and you try to generate the colorized version. Of course, this requires some sort of a semantic understanding, like the color of the nature, the grass in this example, or the color of the cat. If we go towards more complex problems, here is another interesting case where the input is some day image taken under daylight. And the idea is to learn a model to just visualize the scene at a different time of the day, like at night. Another related class of problems are called photo style transfer, okay, where this time you have basically two inputs. One is the input image, and as a secondary input, you take another so-called style image. And the task is to synthesize a stylized version of the input image whose content is like the original input image, but the style is transferred from the given target style image. And lastly, which is more related to the work we will be talking about today, is the so-called semantic image synthesis problem. This time, the input is a semantic layout, and you try to generate a natural image which is consistent with this given semantic layout structure. Here is another recent work from NVIDIA research, which is almost like appeared almost like the same date with ours. Okay, just to wrap up this introduction. So basically, in our work, we are interested in at the intersection of many different topics, like image enhancement, image or video manipulation, and language understanding. So if you consider all the previous examples I have mentioned in the previous slides, basically we are interested in this particular part, which is relatively less explored. And that brings us to the work we will be again talking about today. And the title of our paper is Manipulating Attributes of Natural Scenes via Hallucination. Again, our work has appeared at ACM Transaction on Graphics, and we presented this as SIGGRAPH this past summer. Okay, now let me continue with the related work. Okay, so here I will basically talk about the work on attribute manipulation. So this one is like 7 years ago in SIGGRAPH Asia 2013. We have seen this work, which is to again transfer attributes of a given input image. And this time the output is a translated version of the input based on the date information. Okay. Here is maybe the most relevant related work with ours, which appeared just 1 year after the previous one, where the idea is this time to change the attributes of an outdoor image. And you can just provide some information about different types of attributes. Like, for example, here you can say that what if this scene look like if we have more moist? So here, the main idea of approaching these problems are basically the same. And simply because this was pre the deep learning era, they are applying some shallow methods. So let me just first describe their approach. So BAPE is basically, in order to perform this translation, the methods involve a database of image sequences So the problem basically reduces to matching the input to one of the images in this training data. And once you identify the example, okay, like for example, from this set of training images, we identified that this is the most similar frame that matches with the given inputs, okay. Then we can just look at the target image at the target time, like 9 p.m. in this example. And then they basically apply again some simple image processing techniques to transfer the color from input image to the output based on the target frame information. Again, this is also true for this second work. And this also shows us the main drawback of applying such a data-driven technique, simply because the end result is highly dependent on the matched result. Okay, like for example, for this particular case, this is the target image, matched image. And if you look at the look of the target frame, in terms of its content, it is quite different than the input image. So, of course, this is reflected in the corresponding output, which is, I must say, very poor. So this was one group of related work. Maybe we can also add here as a second class of related work, these photo style transfer approaches. Again, let me remind you once more, we have a content image and a style image, and the task is to transfer this target style onto the input image itself. But of course, again, this requires a visual secondary input to encode the style information. So after talking about all these related work, let me define our problem. Okay, so again, suppose that we are given an input image, and the task is try to imagine this same scene under different conditions. Okay, for example, picture the scene for a second if you were a snowy winter day. And here is the corresponding output. Of course, this is a real scene. You may just notice some small changes in the length of the trees. But in our case, we try to want to train a model that can perform these type of transformations. Now I can continue with the difficulties associated with this problem. Okay, so the first difficulty is that in order to make this translation, you need to take into account the underlying semantics and corresponding scene attributes. What I mean by that? So for example, here, just see these two different positions in the given input image. And if you look at those pixels, so you may notice that they have similar colors, okay? However, if the task were to imagine the scene, like for example, under a foggy day, and consider the right image given on the right, the same positions may become very different under this new situation. Okay, so this is not a one-to-one mapping. It's if you just solely consider the pixel values. Another difficulty is that even if you may have different colors in the original input, because of the attributes, because of the things they imply, all these different colors may map to a similar color. Like, for example, suppose this mountain and the grass region and the corresponding change in this winter scene. So basically, this slice just summarizes our task. So we have an input image like shown on the left-hand side. Here, instead of having a style image like the photo style transfer like works, here we take a set of target transient attributes. Like for example, this could be like I want more flowers or more clouds in the given image, and our framework performs the corresponding translation by reflecting the target changes dependent on these target transient attributes. And here I must add that in order to a little bit simplify the problem, we are also making use of another additional input, which is the semantic layout of the image, just to provide more information about the content of the image. Okay, and now Erkut will continue about the details of our approach.
So as Aykut mentioned, here we are trying to develop an image-to-image translation method, but we are considering some additional conditions, additional information about the scenes and the attributes. Okay, so in that sense, yes, it can be regarded as an standard image-to-image translation method, but please recall that the standard methods can only learn to change a single attribute. Given a day image, it translate them into a night scene, or given an image during summer, it only performs a translation to the winter. So in that sense, for both of those translations, you need to train two separate models. Instead here, we are learning the spatial relationships between two different image regions by using the transit attributes and their semantic classes. So in that sense, it is way beyond than the standard deep photo style transfer methods, because we do not have any other style image as another input. Okay, so in a way, we are trying to take the advantage of the best of both those models, a style transfer method and an image-to-image translation method, to come up with a more generic framework which allows the users to manipulate the attributes of a given scene. So in a nutshell, I can say that our approach includes two separate networks. One is called the scene generation network. In fact, this part is our main contribution. And then there is a separate style transfer network, which, as its name implies, which is responsible from transferring the style of the image generated by our scene generation network. So as a summary, the idea here is to hallucinate alternative versions of the image scene consistent with the target attributes. And once we have this image, we use that as a style image for the next photo style transfer operation. So this is a more complete picture of our framework. As illustrated here, our scene generation network works at a fixed resolution. So we center crop the semantic layout image given as the additional input. And then we resize the source layout to a much smaller resolution, okay? And then the scene generation network is nothing but a conditioned version of a standard generative adversarial network, where the conditions are the target attributes and the given center cropped and resized semantic layout image. So once we hallucinated the scene under the given target attributes, we use this hallucinated image as a secondary input for the style transfer network, which in a way modifies the look of the source image based on these inputs. I will not dive into the details of our scene generation network, but I can say that our architecture is very similar to the pic-to-pic HD model, which progressively generates the image using two generator networks. Similarly, the discriminator network makes use of three let me call it sub-discriminator networks, which work at an image pyramid of three different scales. So as seen here, the conditions, and let me recall, the conditions are the 40-dimensional vector encoding the attributes and the semantic layout as an additional input, as an additional condition. Of course, we also proposed some additional strategies to stabilize the whole training process. For instance, we suggested to use relative negative mining strategy and layout invariant perceptual loss. Let me briefly talk about the details of these strategies. So in relative negative mining, so again, for the discriminator, if you recall, the main purpose is to distinguish a real sample from a fake one. But this is, of course, the standard unconditional version. On the other hand, in our case, we have additional inputs, additional conditions, such as a set of attributes and a semantic layout. So in this relative negative mining strategy, we consider different combinations of these inputs so that we can stabilize the learning process in a more effective way. For instance, we can consider real image, relevant attributes, and layouts as a true sample versus fake image, relevant attributes, and relevant layouts. Or we can consider a real image, but with some mismatching layout or mismatching attributes. Again, to train generative or image-to-image translation models, a common strategy is to consider some perceptual losses to increase the photorealism of the generated images. But this perceptual loss generally considers some pre-trained networks on datasets such as ImageNet. Okay, so in that sense, they are considering additional network which performs a classification task. In our work, instead of using these standard networks and the standard perceptual loss, we considered to use a convolutional network model proposed for the scene parsing problem. And in fact, we used the features extracted by this network a way to provide the perceptual difference between a generated image and the actual one. So this is the first network. For the style transfer network, as I mentioned, we used a previously proposed method. We tried, in fact, two separate network models, but here I only want to talk about the photo style method because it works much faster than the deep photo style method that we also tried on. So in short, this model is composed of two different steps with some closed form solutions. So the first step is a stylization step, and the second step is a smoothing step. So the main purpose of the stylization step is performing the transformation of the original image to a styled image. And for that purpose, it uses the whitening and coloring transformations via feature projections, again, by considering a deep model. The second smoothing step, on the other hand, ensures the specially consistent stylizations via a manifold ranking operator. And this, let me say, this method works fairly good for the case where the content and the style images have similar kind of semantic layouts, which is in that case the reason that we use, because we know that our generated images under the target attributes have a similar semantic layout with the given input image. Of course, for any learning problem, the data set is of utmost importance. And for that purpose, in our work, we created a new data set. And for that purpose, we combined and annotated images from two popular natural scene data sets. At the end, we have around 18K images, which contain 150 different semantic categories in their semantic layouts and 40 transit attributes. Okay. So you can easily see some examples attributes in the middle. So we have attributes encoding the seasons, attributes encoding the lighting conditions such as sunrise, sunset. We have attributes encoding the weather conditions like sunny, warm, moist, foggy, cloudy, etc. And for the semantic layouts, as I mentioned a few minutes ago, the layouts are very rich, encoding 150 different semantic categories. Okay. So, as I said, we consider two separate natural scene datasets. The main reason for that is there is not a single dataset that consists of these two different knowledge about the attributes of the scenes and the semantic layers. So, for instance, the first dataset that we considered ALS 18K within our ALS 18K dataset is the transit attribute dataset. Here, it consists of images captured from 101 different webcams, and the total number of images is around 8,000. And for all these cases, as you can guess, the images are annotated with their corresponding attributes. Okay. But what is missing here is the semantic layout. So Levent did this fascinating work that he manually obtained the semantic layouts for all these 100 different scenes. Okay, so these are some examples for a given single image. As you see, it consists of multiple observations of the same scene under very different conditions. Okay, and as I said, in the original dataset, there are no semantic layouts. So at first, Levent used a semantic parser to predict the layouts, and then he manually corrected those outputs. The second dataset that we considered is called the 8820K, and in fact, we only used a few, around 9,000 outdoor images within this dataset. It is proposed for semantic and instance segmentation. So it consists of 150 different semantic categories in their semantic layouts. And if you compare these two different datasets, you can easily say that 8820K provides much diversity in terms of the scene content. Okay. Again, the quality of the images are better than the previous dataset, which only considers webcams. Okay. But the drawback of this dataset is that it does not have any information regarding the transit scene attributes. So similar to our previous annotation scheme, here we predict these attributes in an automatical manner by using an attribute classifier network that we trained on the transit attributes dataset. Okay, so at the end we obtained this 80K images consisting of both the transit attributes and the semantic layouts. Okay, so let me talk about our experiments. Again, as I said before, our framework consists of two separate networks. We have a scene generation network and a style transfer network. So in our first set of experiments, we only focused on our semantic image synthesis parts on the scene generation network. And as I said, the main idea is given a scene layout and a target set of attributes, we try to generate the relevant images. So in that sense, it's closely related to the standard semantic image synthesis models. And in our work, we compare our the results of our model against two well-known examples, Pick-to-Pick and Pick-to-Pick HD. So our generation network, the main advantage of our generation network is compared to these aforementioned methods is that it can not only generate synthetic images from a given scene layout, but it also allows us to manipulate the look of the synthesized scenes, since we are using transit attributes as additional conditions. So for instance, here you in the left-hand side, you see our results on the scene generation part by progressively manipulating the input semantic maps. And at each step, you can see that our method generates fairly good generation results. Okay, but then once we have a synthetic image like that, as I said before, we have the ability to play with the look of these scenes by changing or manipulating the values of our transient attributes. So for instance, for the last image generated using mountains, trees, waters, grass, and sky, we can play with the attributes as seen in the right-hand side. These are some qualitative comparisons against the baseline models, Pick-to-Pick and Pick-to-Pick HD. Again, here you can easily see that our model not only generates images from the given semantic layout, but it also allows for synthesizing multiple outputs conditioned on different transient attributes. So although here we compare these two sets of approaches, our model is a more powerful model than both of these two baselines. Okay. We also performed a quantitative analysis as well, and our quantitative analysis includes two different sets of experiments. At first, we use automatic evaluation metrics to compare these baseline models and our proposed the scene generation network. And for that purpose, we used two different metrics proposed for evaluating the photorealism of the synthetic images, inception score, and Freshe distance. And again, for evaluating the how relevant the generated scene in terms of the input semantic maps, we considered as standard deep semantic parser and check the segmentation accuracy. Okay, so at the end, we compare both the photorealism of the generated images and the relevance of the generated image in terms of the given scene layouts. And as you see from these results, our method outperforms both of those baselines. Our segmentation accuracy seems to be a bit lower than the baselines, but here let me say that we conjecture that this is simply because our network can generate scenes under different weather conditions, etc., so that a semantic parser cannot segment out these scene elements in a fairly good manner. So we also performed an ablation study for our scene generation network. So as I talked before, we proposed to consider a layout invariant perceptual loss function and a relative negative mining strategy in during the training process. And as you see here, including both of those strategies improves the results, both in terms of the photorealism metrics, inception score and Freshet distance, and in terms of the relevancy that we measure by using the predicted attributes and the predicted semantic layouts. Okay. And this demonstrates a qualitative comparison of the different versions of our models. So you can easily see here that including the relative negative binding improves the photorealism of the results in a positive manner. And again, here VGG is the standard perceptual loss. When it is replaced with a scene invariant version, again, we obtain very nice results. So combining both the relative negative mining strategy and semantic layout invariant perceptual loss, we achieve the best results. So then let me continue with the experiments on the attribute manipulation part, where we considered the whole framework that we developed. Again, as I could mention before, here we have a single baseline model that we can use for comparison, and it is the data-driven method of Lafont et al., which was presented in SIGGRAPH 2014. And here, to make the comparison a bit more fair, we changed the, so again, if I summarize how this method of Lafont works, for a given image, it tries to find the best sequence that contains similar kind of structure, and then it finds the targets the version of the retrieved sequence under the target attributes, and then it performs a standard local color transfer operation. Okay, so to make the comparison a bit more fair, we replace the standard exemplar-based transfer method by the fast photo style transfer method that we considered in our framework. So once the target frame under the target distributions are retrieved, we just use this as a style image and try to perform the style transfer operation accordingly. Okay. Before talking about the quantitative and qualitative comparisons of this method and ours, let me first show you the results of our approach. Okay, so here, this is the input image. Again, we considered the semantic layout. So I forgot to mention, but the semantic layout can be extracted by using an existing scene parser, or for instance, the user can provide the semantic layout manually. Okay, but once the semantic layout is given, the next thing is the target attributes. Okay, so these are only the visual attributes that we considered in our framework. And for instance, we can play with the attributes of this scene. So this is the results where we considered the we considered the same scene under sunset conditions. Okay, you can easily identify the appearance changes. Now the sky becomes a bit orangish. Okay, and the grass and the mountains and the appearance of the mountain and the grass darkens. Similarly, this is the result when we select night as our target attribute. So everything becomes dark image. And this is the result of the manipulation for the snow as the target attribute. So you can easily see that now the grass, you can easily see the snow on the grass. Again, we have a clear sky. Similarly, if we select winter as the target attribute, we have a similar kind of result. Again, these are the results from a single network model. So we only use the input image and are the result of our hallucinated image by the scene generation network, and we perform a style transfer operation accordingly. So for instance, another advantage of our method is that instead of considering a single target attribute, we can consider a combination of those attributes. So for instance, we can increase the attributes, the values of attributes, spring and clouds for the given image. And this is what the hallucinated, manipulated image looks like, okay? Now the sky become grayish, okay? And due to the spring, now the grass looks green. Again, we can consider, for instance, additional attributes such as moist, rain, and fog. And as I'm going to talk about, this is in fact a kind of limitation of our framework. Although the scene generation network predicts a good hallucinated image encoding all those three different attributes, the style transfer network cannot directly transfer the look of this hallucinated image on the given input image. But I can say that the result is fairly good apart from the fog attribute, okay? And this is the result where we increase the value of the flowers attribute. So you can easily see now we have yellow flowers popped out on the grass. We can also have the ability to gradually change between the attributes. So here we perform a kind of linear interpolation between two different attributes. For instance, in the middle, we have autumn and summer for a given scene. So we can gradually change the values of our attributes, and it's a direct effect on the results. If I make a comparison with the previous methods, I can say that our model outperforms the previous work. As you can easily see in these images, the predicted images are semantically more consistent than the retrieved ones, okay? And for the quantitative analysis, we performed a user study which demonstrated that our results are favored 65% of the time against the competing method by Lafont et al. On 60 different text questions. Okay, so in this study, we show an input image and the results of two different methods, ours and Lafont et al., and ask the user which result you prefer under the given target attributes. Okay, so this is a short demo of our work. In fact, Levent had developed a graphical user interface to play with the attributes, play with the results of our scene generation network for a given scene layout. So let me play this short video. Again, here we are showing the results of two different steps. So this is the result for the attribute manipulation. So this is the input image on the right. This is the layout of that image on the left. And here, as you see, by playing with the attributes, the values of the transit attributes, our model has the ability to hallucinate what the image looks like for the given semantic layout under the values of the target attributes. And once they are hallucinated, the fast photo style transfer network can directly transfer the style to the input image. Okay. So for instance, here it increases the fog, it increases the, I think, the sunny attribute, and this is what the manipulated image looks like. So for the scene generation network, for instance, here he adds additional scene elements to the semantic network, and you can easily see the results of the hallucination of our scene generation network. So he adds a mountain on top of the trees, and you see that the results reflects the semantic changes that he made in the semantic layout. As I said, there are some limitations of our framework as well. As I mentioned before, sometimes the star transfer network may give some unsuccessful results, even if the synthesized image by our scene generation network is consistent with the given target attributes. So for instance, the fog example demonstrated in the middle shows this limitation. But for some cases, the scene generation network may fail to generate a good output as well. So the output may be inconsistent with the given target attributes, especially for the night scene. We observed that using just the semantic layers is not enough. You need to provide some additional information about the scene elements that you expect to pop up under this night. Okay, so that's all for our talk. I think we have a separate Q&A session after this pre-recorded video. So I can also thank the organizers for giving us this opportunity. So if you have any questions, we would be glad to answer them.